Hi everyone, this is Chen-Yu from MIT, and today I'm going to talk about extracting gait velocity and stride length from surrounding radio signals. So this is a joint work with my colleagues from MIT, Yuchen, Zach, Rumen, and Dina, and also with my colleague from Boston University School of Medicine, Christine. So if we look at the statistic about aging population, we see a graph like this. The percentage of the older population is increasing dramatically. So 20 years ago in the United States, we have only 10% of the people who is older than 65 years. Today, this number has increased to 15%, and very soon in the next 10 years, this number will be 20%. And as the percentage of older population increases, the percentage of healthcare workers that can take care of them decreases. In the United States, even today, there are 13 million seniors who live alone. So we started thinking about the question, how can technology help take better care of the older population? It turned out that in geriatric medicine, there is a very important metric called gait velocity. So gait velocity is defined as the habitual walking speed. It captures our functional age because as we age, our body adapts and it also changes our walking speed. And the whole interest of this gait velocity in the medical community started with a very important paper. It was a paper that tracked the gait velocity of 34,000 seniors over a period of 6 to 21 years. What they found is very interesting. They found that predicting life expectancy using age, gender, and gait velocity is as accurate as using age, gender, and your whole medical history, including chronic conditions, smoking habits, blood pressures, and hospitalization records. This is very shocking. And besides this, gait velocity can be a predictor for adverse health events, fall risks, and the hospitalization of many other diseases, including congestive heart failure, COPD, kidney failures, and stroke, and so on. It's not only a predictor for these diseases, it can also be used to monitor the progression of these diseases. And because of all of these reasons, today, gait tests are included in geriatric assessment. And in the clinics, physicians use a stopwatch to measure gait velocity. But the problem with this is that we get one measurement only every few months when the old person visits the clinics. While we know that gait velocity is well correlated with all of these health events, but with this infrequent measurement, it's really hard for us to detect changes and intervene earlier. Ideally, we want to monitor a person's gait in the home all the time. But unfortunately, we cannot do that today. So if we look at the current solutions, we have systems that put multiple sensors on the person's body to capture gait, but this is clearly not comfortable enough for continuous use at home. And you may ask, why not just use Fitbit or a smartphone? The problem is that they don't measure your gait velocity. So Fitbit explicitly put on the website say that they estimate your stride length from your gender and the height, and they multiply that with the number of steps to give you walking distance. Smartphone can use GPS to measure distance, but GPS is not that accurate and it does not work indoor. So researchers have proposed using Connect to monitor a person's gait. But the problem is that many people are not that comfortable of being tracked all the time with cameras in their home. So can we continuously monitor a person's gait in an unobtrusive way? What do you guys think? So the answer is yes. Imagine that we can have a device very much like a Wi-Fi router that can monitor your gait using wireless signals. And do that without putting any sensors on your body or putting cameras in the environment. So this is exactly what I'm going to show you today. So this is one of our deployment sites, and the white box hung on the wall, like a picture frame, is our sensor. So this sensor transmits wireless signals to the environment and it analyzes the reflections. And by understanding how human motion interacted with these reflections, it can capture a person's gait. So let's say when a person appears, the device will start monitoring and tracking the person's walking, and then it will compute the gait velocity and also the length of the steps of the person. So here, the person's gait velocity is 1.05, and the stride length is 0.75, which is normal for him. So this sensor is called white gait. It's a first system that can measure gait velocity and stride length continuously using wireless signals. And the main challenge in doing this is really that we need to identify walking periods from other type of motion. And we need to develop smart algorithm to extract meaningful gait metrics from these measurements. So it's a standalone sensor that's tested and deployed in 14 homes throughout a period of 1 to 3 months. So before I can tell you how gait work, I need to tell you a little bit about wireless signals and what we know today that wireless signals can do. So when the device transmits a signal, it reflects off the person's body. And by measuring the time it took the signal to travel, we can get the distance from the person to the device. And if we measure this distance from different antennas, we can get two distances, and it will give us a rough estimate of where the person is. So this is great. We get the locations. You might think that to get the gait velocity, we can just measure the change in location over the change in time. However, this does not work. If we're simply looking at the velocity of a person over time, this is what we see. It's really unclear what these up and downs mean, and in fact, the person was walking only during these 2 periods of time, the shaded green periods. And for the other periods of time, the person was not even walking. So how come we ended up with such bad measurements? The reason is that for all of these location-based reflection measurements, they only give you like a rough estimate of your location. They're not intended to give you like an accurate measurement of a gait velocity. So let's say this is a person, and the person's actual location is the red dot here. So these systems will return like a measurement of the location with an area up to like 1 meter. And more complicated than that, these systems takes only one reflection point as your location. So when I move my arm here while I'm talking, these systems will capture that motion and say that I moved to a new location. And also they have no notion about like whether you move your arm or you move your head or you move your leg. So any motion here will register a change in location. So that's why we get a very noisy and bad measurements. And if you just directly calculate the velocity, it wouldn't give you a meaningful measurement. So what can we do? The real challenge is really that we need to identify periods when the person actually walks from all other type of motions. This includes like body part movement while I'm talking, and also the whole body motion when I'm doing activities other than walking, like cleaning, dressing, and cooking. And after that, we need to design algorithm to extract meaningful gait metrics from these walking periods. So let me show you the first challenge. How can we identify walking from other activities? So our intuition is that instead of looking at the velocity directly, we can analyze the spatial structure of the location point. So we want to capture some criteria of a good walking period. It includes like the person needs to move a significant amount of distance to be counted as walking. And also, we don't want to include periods when the person was walking with distractions or interruptions. So let me show you how we can do that. Here, I'm showing 2 periods of the location data. So at the left, the person was walking, and at the right, the person was cleaning his desk. So you see like he's moving around. If we use a circle to bound these location points, it's clear to see that the left one has a bigger displacement than the right one. But the problem is that, let's say the person paused in the middle of a walking. Then the green circle here will mistakenly think that it's a good walking period. What should we do here? So in this work, we use a sliding window to estimate the diameter of location points as a function of time. Let me show you what I mean by that. So let's say we have a 4-second window. In the first 4 seconds, the person was still moving in place, so we can use a small circle to bound the location point. And in the next 4 seconds, the person started moving, so we need to use a larger circle. And as the person moves, and also as the location point in the window changes, this circle changes. And when the person pauses, we can use a small circle to bound the locations again, and so on. If we look at this diameter, the diameter of these circles over time, it's now very easy for us to distinguish between walking with interruptions or pauses, in-place motion, or like a good walking period. So this is great. This is a great way to analyze the location data. But for continuous monitoring in home, we have so much data coming in real time, one measurement every few milliseconds. To consume all of these data, we need an efficient algorithm to process them. If we use a naive algorithm to process it, it will take OK n squared steps, where k is the total number of time steps and n is the number of points in your observation window. In contrast, we implement a streaming projection algorithm that can process the data in real time and co-log n. Because of the time constraint, I encourage you to read the paper for further details. So now, let's go back to the example again. So I'm showing you the same velocity over time, but now augmented with the estimated diameter over time. Now with the diameter, we can clearly see that there are some periods where the diameter is small. This is when the person is either stationary or moving in place. And at the end, you see changes in diameter, but not significant enough for us to account it as walking, and also it contains pauses in between. So now we can easily remove these periods and get the walking periods we want. So are we done? Not yet. So as I told you earlier, after we extract these walking periods, we still need to use algorithm to get meaningful gait measurements. To illustrate the issues, let's zoom in on one of these walking periods. So here, I'm showing you the velocity as a function of time at a walking period. So if you look at the overall trend of this velocity, naturally, in the beginning, you have an acceleration phase, and at the end, you have a deceleration phase. If you take the entire period to compute the gait velocity, you wouldn't get a meaningful measurements. And in fact, in the clinics, physicians remove these acceleration and deceleration periods in calculating gait. But how can we zoom in on this period with this data? Our idea is that walking is actually a very periodic process where a person put one foot down after the other repeatedly. So especially if you look at this middle part, you can clearly see that velocity is oscillating around a stable value. And with this intuition, we design an algorithm that iteratively zoom in on this stable phase. So this will be the first iteration of the algorithm. This is the second, and it converges. So after we extract the stable phase, we can now compute the gait velocity as a median velocity inside this phase. So far, I told you how we can extract gait velocity. And now, after we extract the stable phase, it's also easy to extract the stride length. So now if we look at the stable phase, it's very clear to see that the periodicity in the walking and the up and down here are nothing but like a person's steps. If we take a Fourier transform of this period, we'll see a clear peaks in the frequency domain, and this is the person's stride frequency. And now by dividing the gait velocity with the stride frequency, we can get the person's stride length. So I want to show you some results from our evaluations. In the lab experiments, we recruited 18 subjects, and we used a VICON motion capture system as our ground truth. So the VICON system is a system with multiple infrared cameras that can track the markers on your body with sub-centimeter accuracy. And it gives us a ground truth of the person's location all the time. For walking identification, we emulate a home scenario in this VICON room, and we ask the subject to perform daily activities such as cleaning the desk, sweeping the floor, or moving objects from one desk to the other. And at the same time, we ask the subject to leave their phone on the table. We trigger walking by calling their phone in unspecified times and without their notice. And the subjects were asked to pick up the phone whenever it rings. So let me show you the precision and recall of our walking identification. The precision is defined as out of the total number of detected walking periods, how many of them are true. And the recall is out of all the true walking periods, how many of them are redetected. So here we can see that the precision is 100% and the recall is 96%, which is very accurate. And in designing the algorithm, we choose a parameter to be more lenient or more strict on the precision because we want the extracted gait metric to be accurate afterwards. So after we extract these walking periods, we can now compute the gait metrics. Here I'm showing you the median accuracy across 18 subjects. And for gait velocity, we get an accuracy of 98%, and for stride length is 96%. So this shows that Gait can measure gait velocity and stride length using wireless signal very accurately. So besides the accuracy, I also want to understand like how users feel about this device. Do they feel comfortable having them at home? So to understand this, we deploy devices into people's homes. So this is one of our subjects' home, and the white box there is Gait. We deploy with 14 subjects over a period of 1 to 3 months, and the goal of this study is to evaluate if users feel comfortable using such device at home. And to understand this, we ask these 2 questions. After 1 month of deployment, we ask them, has the device changed the way you normally live? So we ask this to just make sure that they feel comfortable about having this device for continuous monitoring. And we also ask, can we replace this device with a similar device and measure gait metrics, but using a camera or Kinect? So here are our responses. So none of the people feel that this device obstructs the way they normally live. And some of them say that in the first few days they are aware of the device, but soon it blended into the background. For the second question, only 3 people agree to replace Gait with a camera-based system. So this shows that we have very high user acceptance. So finally, I want to show you some very exciting results from our real deployment. So this is the data from a subject with multiple sclerosis. On the y-axis, I'm showing you the daily average gait velocity. And on the x-axis, it's like different dates on February. So you can see there is a degradation in gait velocity at the end of this month. And after that, what we learned is that a fall happened on February 25th. So, like, medical research has shown that fall risk is very well correlated with changes in gait velocity. So you can imagine that in the future, if we can incorporate this data to show it in doctors in real time, they could have detect changes and intervene properly. Of course, we build on password in this area. So I already mentioned to you some of the existing systems that measure gait using wearables or Kinect or cameras. However, they could be cumbersome, inaccurate, or raise privacy issues. And we built on password on wireless localization and also detecting activity using wireless signals. However, we present the first system that can extract gait velocity and stride length using wireless signal in the homes, and like without interfering in the user's life. So to sum up, today I presented to you Gait, the first system that can measure gait velocity and stride length in the home continuously using wireless signal. It's very accurate and it's easy to use and with high user acceptance. We're now working with medical doctor to incorporate the sensor data into the analysis of disease progression. With that, thank you very much.
Hi, Matt Lee from FXPAL. This is great work, so thanks for presenting it. 2 questions. One of them was you showed the mounting of the sensor. It looked like people walking parallel to the sensor.
Yes.
No,
this is just for video shooting purpose. So actually one of the biggest difference from us with PyWork is that we don't need the user to walk on a specific path. So the user can walk freely at home, and because we have the algorithm detect when they are walking and extract gait metric from that, so it actually gives a lot of flexibility. And that's why we get also high user acceptance rate.
Yeah, great. My second question was about, can you distinguish between different users if there are multiple residents in a home?
Yeah, actually that's a very interesting question. So actually Gait tells us a lot more about a person than just the velocity or stride length. In our real deployment, so we have deployed at places where there are old person, like a nurse, like visiting occasionally, and we can clearly see like from the way they walk, or just from their gait velocity, like you can clearly tell that the old person walked very slowly. And occasionally you get few measurements of very high, high gait speed, and those are the nurse visits. So from that, we can tell the difference between people. And we believe that there are more information in these location data that we can try to learn from and to give us better identification of people.
So you can also get localization roughly? That
So
kind of data?
yeah, so we get the location of the person. As I showed you earlier, you see those dots in the space. So those are the data that we operate on.
Cool. I guess I'll ask one last question. It was
Sure.
about, a lot of people walk with assistance, with a cane or not.
Yep.
It would be interesting to see if your system can also detect whether they're walking with assistance or without, and that could be very useful clinical data.
Yeah, yeah, that would be very interesting. Thank you.
Other questions? Hi, I'm Philip Chernowski from the University of Paris-Saclay. This is a very interesting presentation. I was wondering, so you're saying there's medical evidence that this is a sort of very good measure, sort of predictive measure of health. And I guess it's well known that once you start, measuring people or giving them the scores for things, then they start modifying their behavior to optimize that measure.
Yeah, exactly.
And I was wondering if you have had any reflection on whether this will continue to be a useful thing to measure if it's something that people have in their home and their doctor is getting all the time.
I see. So actually from our experience talking with doctors, they want to measure this in people's home because exactly as you said, when people come to the clinics once, maybe half a year, they want to perform the best of their walking. And sometimes it actually biases the how the doctors will interpret the data, and they want to know how they're doing in the homes, and basically that's their habitual walking. So I hope that answered your question.
Yeah, sure.